So welcome to this course. This course is about groups. Many of you have seen what groups are, but many of you were also scared when groups were being taught in your class. Nevertheless, we are always happy with puzzles, right? There are many interesting puzzles which are associated to groups, and we are going to learn in this course. Symmetry is another aspect which fascinates everyone, which is everywhere in science, which is there in nature, and in fact, groups were originally created to understand symmetry, and it was actually symmetry of equations. We will see all that in this course. And motion is key word. Usually motion is associated to physics, but the word motion here essentially represents what is called action of groups, group actions. You might not be aware of what actions are. Some of you may be scared of what groups are. Doesn't matter. In this course, we are going to learn groups right from the scratch. We are going to learn why groups were created and what are the applications of groups in other walks of life, say puzzles or symmetry or many other things. So for quite a long time I am not even going to define what group is. So if you don't understand what group is, doesn't matter. First we have to see the examples of groups which are there, which were there right from the beginning with us. Have you seen this? It's a beautiful puzzle that I used to play when I was a kid, and I have one version, this one. You know what we are supposed to do here? This jumbled, the small tiles are there jumbled from 1 to 15. I just unjumble it so that everything is on place. Everything is from 1 to 15. What does it have? What does it have to do with groups? Well, there is something called permutations. Permutations are very basic examples of groups. So the set of all permutations, it has the structure of group. So what is the meaning of permutation? You have various objects. Say you have three things, just name them as A, B and C, and then you make some shuffling. So shuffling is the permutation. After shuffling, C may come here, maybe A comes here, B comes here, or maybe after shuffling A remains here, C comes here and B goes there. So there are various ways in which these 3 points can shuffle themselves. Shuffling is very much there when we play cards, like card games. So shuffling is permutation. So there is a lot about groups already there in this puzzle. We will see that in this course. And the key word is actually even permutation, because here tiles, all these tiles which are there, they are not allowed to move freely, because there are some restrictions. There are 4 sides are there. These tiles cannot just go out and permute themselves freely. There are some conditions. In fact, what turns out is that these are what are so-called even permutations, which are relevant here. Again, this thing, after this kind of thing, I came across this, which you must have seen, you must have played, you must have seen videos of these things. This is 2 by 2 Rubik's Cube. This is 3 by 3 Rubik's Cube. Again, what is happening here is permutation, right? But again, this is restricted permutation. Permutation is restricted. It's not that these small cubes are just falling apart and any kind of permutation is happening. No, it's not the case. There is some restriction. There are some rules by which these permutations can happen. For example, if you take this one, the middle one, the yellow middle is not going to move at all, right? It remains exactly at the same place. So there is some restriction to the permutation that we have here. So in fact, if you consider the solved cube as one state and then I permute this, after some time I permute again the permuted version. So what am I doing? I am considering the composition of two permutations. The composition of two permutations is again a permutation. I can do a permutation and I can reverse it back, right? So for a permutation, there is a reverse permutation. These are some of the properties which groups have. I am not defining groups now. Those who know groups, they will understand that composition of two things is again of the same type. That is one of the properties of groups. This is quite interesting. Some of you might have played this game. This is called Peg Solitaire. Some people call it Brain Vita. And this permutation which is happening, but there is something quite interesting which is called checking of parity check. So some question I am going to ask later on concerning this particular game, this particular puzzle, and it has not much to do with permutations, but it has something to do with the abstract group law. So using abstract group law, I am going to explain something quite interesting about this puzzle. So you have to watch. And then these card games, we have always played these card games. Again, what's the keyword? As you know, permutation. Permutation is coming again and again. And with card games is probability which is assigned, probability which is associated. So, well, groups are associated to, groups are connected to probability as well. There is something called graph of the group, and you can move in a random fashion. You can do random walks on groups, and those are also quite interesting topics. But so far, we don't know what groups are. I am just giving you examples of groups before actually telling you what groups are. Nature has very much symmetry. Butterflies, leaves, trees, so many aspects of nature have symmetry. And as I said, groups were originally created to understand symmetry of roots of polynomial equations. We will come to that point. So symmetry. And when we grew, maybe when we were in primary school, we saw these operations: addition, subtraction, multiplication and division. And what is there is arithmetic. So if you have two numbers, you add those numbers, it's again a number. So let's start, let's take the set of numbers to be, say, the set of integers. If you add two integers, it remains an integer. If you subtract one integer from another integer, it remains an integer. Similarly, if you take non-zero rational numbers, you can multiply two non-zero rational numbers, and you can divide by non-zero rational numbers as well. So arithmetic is there, and arithmetic has a lot to do with groups. Lots of examples of groups come from arithmetic. We will see that. But groups are beyond that. This we have seen right from our high school, this formula. This is to solve quadratic equations: minus b plus minus square root of b square minus 4ac divided by 2a, and there is some symmetry which is here, and that is why I am saying that there is some group which is there in the picture. The symmetry of roots. There is symmetry around minus b by 2a. There is plus, and the same amount is there in minus. There is symmetry in the expression. So symmetry of expressions has something to do with groups. Any kind of symmetry has something to do with groups. And the symmetry of these expressions, these polynomial equations, these roots comes under the branch of mathematics which is called Galois theory. Galois theory is a bit advanced topic, we are not going to touch it, but nevertheless it is worth mentioning that Galois theory is essentially the origin, it's there in the origin of groups. And we remember about complex roots, right? So complex roots occur in pairs, we know that. If iota is a root, then minus iota is also a root for the polynomial equation which is having real coefficients. If real coefficients are there, the conjugate roots will occur in pairs. So this is a root, then this is conjugate, this is root, then this is conjugate. What is there? There is symmetry across this axis, you call it x-axis, there is symmetry, right. So that symmetry is again captured in groups. So symmetry and of course Galois theory, as I said. One very important aspects of Galois theory is what is called insolubility of quintics. It says that you cannot have a formula which uses these symbols. This is addition, subtraction, multiplication and division, and this is called radical. Radical is square root, cube root, nth root. So using these symbols you cannot create a general formula which can give you solutions of degree 5 polynomial. Although we know that if the degree is 2 and not 5, then you have a formula as I showed you some time ago, a couple of slides ago, but in general there is no formula for this, and the ideas which are involved in proving this big statement, insolubility of quintics, they come from Galois theory and they come from what is called Galois group. So group theory is there. Group theory is there in proving things which are not directly related to group theory. It seems the group theory as we see during our first course, but then it has some connections with other things in mathematics. Okay. At much higher level, groups are also there. One very important use of groups is in distinguishing topological spaces. It is just an example I am mentioning. In topology there is something called fundamental group, there are certain cohomology groups which can be used to distinguish various topological spaces. To each topological space you associate some group, and you do this assignment in such a fashion that if these topological spaces are homeomorphic, then the associated groups are isomorphic. So if the associated groups are not isomorphic, then you can easily conclude that the given topological space are not homeomorphic. So there also one uses concept of groups. So group theory, as I am saying, it is there in abstract mathematics, it is there in physics, it is there in many puzzles, and the interesting part is going to be there in group actions that I am going to explain after some time. And then in higher mathematics, at research level and postgraduate level mathematics, we learn what are called Lie groups and algebraic groups. Lie groups are quite interesting for physicists and people who work in group theory or algebraic geometry, and maybe understanding polynomial equations. They are working, they have algebraic groups as topic of interest for them. Okay, so after all this, so what did we do so far? We have kind of seen examples of groups, although I have not mentioned to you what a group is. I will come to that after some time, and before I do that, I would like to show you an interesting experiment, and this experiment, as you can see, involves 3 glasses, and I am saying that this interesting thing has something to do with groups. So let's see what happens. Here's an interesting puzzle for you, and I am going to show its solution. So I have these three glasses. I have put them in inverted position, and what's the purpose? Purpose is to keep eventually all of them upright. But there is a rule. What's the rule? At a given point of time, I have to pick any two of them and I have to change the position of them. And then I pick any two of them, change their position. I take some other, change their position like this. So I hope the rules are clear. There are three glasses. At a given point, I am supposed to randomly pick two of them. So can I make all these three glasses in the upright position after some time? So if I do this couple of times, it seems I can't. I am back to the same thing. Let's try more. This, 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 this. I'm back. So it seems I can't. How to prove that it is not possible? I am going to mention after a couple of lectures concept of parity, and also during the study of group action, during the discussion of group action, we are going to learn the notion of orbits, and using both the notions I will show that using group theory you can easily understand that why, if I follow this rule where I am picking two and changing their state, changing their orientation, then just by doing that again and again I won't be able to keep all three of them in upright position. So I hope you enjoyed watching that puzzle with the three glasses. Okay, so what are the keywords that I have uttered in this lecture so far? Permutation, which is just shuffling. Symmetry. So what is symmetry? So here is my definition of symmetry. It is doing something that you cannot detect. Sounds mysterious. So here is something that I am going to do which you cannot detect. Here is one A4 size sheet. That's a rectangle, right? That's a rectangle. I am going to do something on the back, and probably I am doing something, probably I am not doing something, and then I am showing you back. So did I actually rotate it? Did I actually flip it? Can't make out, right? Okay. Now if I do something, you can make out, yes, I have rotated this rectangle by 90 degree. So what is symmetry? So given this rectangle, if I flip about x-axis, this is, let's call this horizontal thing as x-axis, vertical thing as y-axis. If I flip it about x-axis, that's a symmetry, because had I done it on the back side, you would not have detected it, right? So if I do it, it remains, it looks the same. If I do it like this, it's clear that it's different. So flipping about x-axis is symmetry. Flipping about y-axis is also a symmetry. What else? Well, doing nothing is also a symmetry. I am not doing anything, that's a symmetry. And if I rotate by 180 degree, that's also a symmetry. So what I showed you was this. I have a rectangle, I have these axes, x-axis, y-axis, and then if I don't do anything, I am denoting it by 1. or if I flip about x-axis, or if I flip about y-axis, or if I rotate by an angle of pi, all these are symmetries of a rectangle forming. So that's what I said. We do something which cannot be detected, that's symmetry. Rotation, of course, rotation as we have, say, you have a sphere and I am rotating the sphere, that's an example of symmetry. And rotation is also a keyword that I have been using here. So revolving about an axis is rotation. And permutation is also a kind of symmetry. It can be thought of as symmetry of discrete points. So suppose I have these, I am just using again these three classes. There are three different points. They are not associated to each other, they are not bound to each other, they are discrete objects, and when I permute them, that's a symmetry. See, if I just do it in the back and I show you have I done something, you will not be able to detect, right? So permutation is a kind of symmetry, but the symmetry of discrete points. To understand rotations and permutations, one of the important objects that we have is matrix. It's not very relevant here, even if you have not seen matrices, don't be scared. And as far as rotations are concerned, one can also think of rotations as multiplication by complex numbers. That's rotation in 2 dimensions, but for rotation in 3 dimensions, there is a concept of quaternion algebras. We won't be much worried about this in this lecture. Okay, so here comes now the formal part of the course, formal part of this lecture, which is about definitions. So what are groups finally? We have seen various examples. We have seen that groups are related to permutation, groups are related to rotation and all that, but what exactly are groups? So here it is time for us to learn all those things precisely. Okay, so for that let me come back to the symmetries of rectangle. I had written 4 things. 1, fx, fy and r pi, right? I'll write it here as well. 1, fx, fy, r pi. So here is the thing, if you have a symmetry and compose that symmetry with another symmetry, it again remains a symmetry. What do I mean? I mean that if you have this rectangle, I flip it by x-axis and flip it by y-axis. I am flipping it about both the axes, x and y. What I have is again a symmetry, right? So let's see what is happening exactly. So for that, if you carefully look, I have marked this as a front and 1, 2, 3 and 4. I am flipping about x-axis and after that I am flipping about y-axis. Did you observe what has happened? When I am composing the two, fx and fy, what I am getting is actually rotation by pi. So fx composed with fx composed with fy is actually rotation by pi. And if I compose doing nothing with anything, what I get is that anything. So 1 composed with fx is fx, similarly 1 composed with fy is fy, 1 composed with r pi is r pi. And in same fashion I do it here. 1 composed with fx is fx, 1 composed with fy is fy, 1 composed with r pi is r pi. And what is fx composed with fx? That means I am flipping about x-axis, and once more I am flipping about x-axis. I am back to identity. So I am writing 1 for that. Similarly, when I composed Fy with Fy, I have 1, and if I rotate by pi and again rotate by pi, I have rotation by 2 pi, which is just identity position, rotation by pi, rotation by pi. So I am again having 1 here. So what about Fx composed with R pi? And that would be interesting. So I have Fx and I am composing it with R pi, that is rotation. You know what do I have? I actually have, do this experiment, I have just Fy. I'll just flip it once and show you, just Fy. And similarly with this, if you do experiment, what you get is that Fy composed with Fx is R pi, Fy composed with R pi is Fx, R pi composed with Fx is Fy, and R pi composed with Fy is Fx. So let's look at it carefully. What do I have? I have 4 objects. I have a set. Let me call this set as G. This set has 4 objects, 4 elements. And there is natural way to compose these elements, right? And composition goes in very natural way. I am composing these elements and I am able to write composition table. I am able to give a composition law which is motivated by doing one operation after another operation. So let's try to see this at with a larger perspective. So I am able to compose 2 objects. Well, we have been composing these objects, various objects, since our school when this set was given to us, the set of integers. We were composing, isn't it? When the set of integers was given to us, we were adding integers. And what was the law for, what were the properties of those at the addition? If we take 2 elements from this set, add them, answer is again of the same type, right? So here composition law is there. What are the properties of this composition law? There is a neutral element which does not do anything. And then for every symmetry, there is an inverse symmetry. What is inverse symmetry? You do this and after that you do something so that you have 1. You are doing this, you do something so that it is 1. So here I would say it like, I would say that Fx inverse is again Fx, because after Fx, if you perform Fx again, you are back to identity. Okay, and same is true with Fy here, same is true with R pi here. However, when we have integers, doing nothing is 0 as far as addition is concerned. 2 is here. What should you compose with 2 in order to obtain 0? Minus 2, right? So when we observe all these properties, we can write the definition of a group. You take a set and you pick 2 elements from this set. How do I pick? Well, I pick 1 element from G cross G, right? So I take 2 elements from this set, call them G and H, and to that I assign something in the same G, and I just simply call it GH. And then there should be some properties. What are the properties? 1, there should exist a neutral element, identity element, which does nothing. For every element in this set, there should exist an inverse. That means I am just denoting the inverse by G inverse. So, and inverse, what's the meaning of inverse? So that if I compose that element in either of the directions, left or right, what I get is the neutral element. That was the property that our symmetry group for a rectangle had. And third thing is what is called associativity property. So if I take 3 elements, so suppose I take G1, G2, I compose them according to this operation, this law, and then I take G3, or I could have done G2, G3, I could have composed it according to this law, and then I could have taken G1. The answer should be same. So if on a set I define an operation like this which has these 3 properties, then I call it a group law. And we have seen examples of group laws. The set of rectangles, set of symmetries of rectangle is a group, it is following group law. All integers along with addition again is following group law, because 0 is identity element, additive identity, minus is inverse, and the associativity is also followed in that law. Quite important property of groups is group action. As I say, groups are bound to act. Unless they have an action, unless they have nice applications, they are not interesting. So we are also going to see what group action is, and again for that group action I will take the example of symmetries of a rectangle. So what have we seen in this lecture? We have seen various examples of groups without actually realizing that they were groups, and then we saw formal definition which came through the example of symmetries of rectangle. And as I am saying, groups are bound to act. So group action is what we are going to learn in the next lecture. So group action is a key word, and that will remain the key word for quite some time. We are going to learn orbits and stabilizers and orbit stabilizer lemma. It is quite interesting, and we will see very interesting applications of these things. So stay tuned. We will see you again.